Okay, we've moved on now. We've got general overview of the atmosphere, and we've talked about energy arriving in the atmosphere. So now we're going to move on to the next part. The very first element we deal with in weather is temperature. Every day, you probably wonder, well, what's the temperature going to be today? What kind of clothes do I need to wear to go outside to be comfortable? So we're going to explore a little bit about how that temperature changes from day to day, even from hour to hour, and why. So, with that, what causes the heat transfer within the Earth? And we're going to define heat transfer in just a second here. So first, let's understand what temperature is. Every atom, every molecule moves a little bit. The more it moves, the more kinetic energy it has, which is energy of motion, and the more it moves, the higher the temperature is. The temperature is directly proportional to kinetic energy. So in other words, if the air is 110 degrees, those molecules are moving crazily. If the air is minus 20, they're not moving so much. So that's all it is. Temperature is just directly proportional to that. And heat is just energy in transit. In other words, one day we know the temperature may be 70 degrees, and the next day it might be 40 degrees. How did that heat change? What caused that temperature to drop like that? So heat is just that energy in transfer. And we need to understand that if we're going to be able to understand how temperature changes. So one of the things is that there's a temperature gradient. There's temperature gradient in the atmosphere. There's temperature gradient, for example, if you're cooking food and look over a hot stove. If you go out in the direct sunlight, it's going to be a lot hotter than if you're in the shade. There's a temperature gradient there. So this is basically just a change in temperature over a distance. So the faster the temperature changes over a distance, the stronger the temperature gradient. Let me repeat that. The faster the temperature changes over a distance, the higher the temperature gradient. You're going to see a lot with gradients in this course. I want you to understand that. And heat always flows toward lower temperature. It's trying to eliminate that gradient. Guess what? The Earth, if it had its way, would eliminate all temperature gradients. There would be none. The Earth would be the same temperature everywhere. However, that is not the case because we've seen energy flows into Earth very differently in different parts of the Earth. So we have temperature gradients. So how does this heat flow? How is the heat transferred? Well, it's transferred through radiation, which we talked a lot about in the last chapter. Conduction, convection, or latent heat. So radiation just means energy transfer, like from the sun, like from a hot object. So that is just one means of moving energy around. Conduction is another. You may have seen where it gets so hot in the summertime that somebody tries to boil an egg on the concrete or on a patio or something. Fry an egg. That's conduction, where the surface gets ridiculously hot, and then the lowest layer right next to that surface, connected to it, heats up from that surface. If you were to put your hand on a hot stove, I hope you don't, that would be conduction, as that heat is transferred into your hand. In fluids, and the atmosphere is a fluid, considered a gas, it's a fluid. You have convection. If you ever watch water boil, you'll see little bubbles come up at times. That is convection. That's heat being transferred from the bottom of that pot of water to the top. That is convection. The same happens in the atmosphere. Heat will rise from the surface, up, cool, and come back down, cooler. So it's just transferring the heat up and down. You can notice it when you look at cumulus clouds. They're really a great example of convection in the atmosphere. And then the phase changes, latent heat. Okay, if you ever think about it, if you have water and you're boiling it, you're adding heat to that water, correct? To make it into a gas. Because when it boils, it releases water vapor. So if you added heat into it to make it, that means that you've added energy into that. So there's more energy in water vapor than there is in liquid water. And guess what? If you melt ice, the sun hits it, warms it, melts it. It is adding energy to make it a liquid. So as you go from a solid to a liquid to a gas, energy is being added to that liquid, to that water. If, on the other hand, you go from a gas to a liquid, well, since the gas had more energy initially and you're going to a lower energy state, energy is released. It actually heats the atmosphere. So, evaporation, for example, if you're evaporating a pool of water, cools the atmosphere. If I am melting ice, I am also cooling the atmosphere. However, if I'm freezing, believe it or not, I'm releasing energy into that atmosphere. The same happens when clouds form. They release energy into the atmosphere. All right. The oceans, think about it, they cover 75% of the Earth, roughly. So if you live near an ocean, you're going to have probably more of a maritime climate. So what does that mean? Well, the oceans heat a lot slower than land. So if I live near the ocean is going to remain cooler probably than the land. And on the west coast of the United States, where the winds are coming mainly off the water of the ocean, the water is relatively cool. We don't see a lot of temperature change from winter to summer because of the oceans. Now, if I'm in the middle of the country, and you could say St. Louis is here, or you could look at Ohio, all of that, West Virginia, they are continental climates. What that means is land heats quick, land cools quick. So you get a much more extreme temperature change between the seasons. Here is the atmosphere. And when you look at all the radiation balances that go into it, and it is ridiculous. All of that relates to how, and the heat flux and everything is relating to how temperatures change. So, heat transfer from conduction and convection is one way of changing and looking at it. It produces uplifts, clouds, and then you combine latent heating, which as the clouds are condensing, they're releasing heat, even produces more heat. So in a thunderstorm, heat is being released, helping the air to warm. Interestingly, we can look at the Earth over the whole, and you see there's a whole lot more radiation that's absorbed in the tropics than there is in the poles. And all the time, we're trying to transfer the heat from the tropics to the poles. We're trying to warm the poles, cool the tropics. It's a constant battle. How do we do that? With air mass exchange, storm system, ocean currents. What are air masses? Air masses are a large mass, large quantity of air covering thousands of kilometers, and they have uniform temperatures and humidity typically. All right, so if you lived in Canada, in the wintertime, you have a snow cover, you don't have a lot of sun coming down, you have very light moving air, we'll say. What are you getting? You're getting a very consistently cold, very dry, because there's no oceans up there, air mass. That's a continental polar air mass. Now, let's go off the southeast United States. And what do you have there? Well, the Gulf Stream's out there. So you have a pretty warm ocean all year long. Temperatures in the 70s, even 80s in that ocean, sometimes warmer. I sit a mass of air over that area. First, I'm getting water vapor lifting into the air. And second, I'm getting heating from the surface. Also, I'm closer to the equator. I have more sun, direct sunlight coming in. I am getting what is called a maritime tropical air mass, warm, moist. Also, storms are very great contributors. Matter of fact, tropical storms and hurricanes are the greatest contributor of moving heat towards the North Pole. So all these imbalances are what causes the weather. They set the air in motion, and they cause this change in seasons. They cause our storms. They're the reason we have weather. If the Earth had uniform temperature, not so much. Now here's a daily budget of temperature. Well, think about it. We've talked about ultraviolet radiation coming in from the sun. When is that the strongest? Well, it probably reaches its peak at noon, but it continues into the afternoon, right? So that air is heating, that radiation is heating your air all day long when the sun's up. Now, temperature. Temperature begins to go up. It's releasing infrared radiation. However, there's more radiation coming in from the sun. So that air is still warming. At one point, late afternoon, they reach the same. There's the same amount of infrared radiation going out as the ultraviolet radiation coming from the sun in. That's your max temperature for the day. Late afternoon, normally. Now, after that, all right, the air is pretty warm relatively at that point, so it's going to produce a maximum amount of infrared radiation going out. So it's going to cool pretty doggone quickly. And then the infrared radiation is going to go down, not cool, and the air is actually not going to cool as fast later in night. So you can see that's how a normal, bright, sunshiny day, clear day, your temperature curve would look. Now, there's another part to all this. Albedo. What does albedo mean? Albedo, we talked about it last chapter, just reflection of the sun's radiation. Bare ground, lots of vegetation, lots of water. That absorbs the sun's radiation, allows it to heat up. However, you go in the desert, light sand, that's pretty decent albedo, a lot of reflection of the sun. Even if the sand heated during the day, at night, it's going to release a lot. Now, if you have snow or ice, like you do over the North Pole or South Pole, or in the wintertime after a snowstorm goes through, you got lots of high albedo, lots of the energy is released into the atmosphere and back out into space. That is why it stays so daggone cold after it snows for a little while. There has to be other factors that allows it to warm up and melt the snow. But at first, this also causes, and snow is an excellent emitter of infrared radiation as well. So what does it do? Even cools even more at night. That's why when you're looking for the coldest temperatures, you want a night where you have plenty of snow cover and clear skies. Balance. We've documented them through the years. This is just one of Washington, D.C. There's documents on St. Louis. There's others. If you're in an area that has lots of buildings, you have an urban heat island effect. So it gets significantly warmer. I worked in Washington, D.C. for a number of years. The airport, National Airport, is downtown Washington, D.C. If you go back through the climate records, you can actually see how the area built up with time and see a change in temperature with time, where it doesn't get as hot, as cool at night as it used to. You can really see that. It's very significant. So, with that, to show you a couple little things here. This is the current weather map. So let us look at advection. Look right now. There's a cold front coming through Indiana and Illinois here. What do you see? Northwest north winds behind that front. If you go upstream of there, 60s. Down on the other side of the front, temperatures are in the 70s. That is cold advection. That wind is pushing colder air in. So that is a classic example of cold advection. I also wanted to show you next week. This is a forecast. And a lot of the models are forecasting this. This is temperatures between 21 and 27 degrees Celsius at 850 millibars. About 4,000, 5,000 feet up. It's a great way to look to see how warm air is coming. Kind of harder to spot sometimes on the surface, but if you look aloft, it kind of looks a little bit easier. Remember, the atmosphere is three-dimensional. So you can see very strong warm advection into the Midwest, Kansas, Oklahoma, Iowa, early next week. And it continues. The heat is just building out there. And that is being transferred to the east as well. That's why later next week, you will be getting a heat wave in Ohio and West Virginia. That hot air is being advected in from the southwest into your part of the United States and across the Northeast. So that is a major influencer on bringing in warm air to you. So hope you got a little bit out of how temperature changes. And let me know if you have any questions.